Another application of integration that we're going to look at is called arc length. And so arc length is sort of related to, it's the length of a curve. If we recall from geometry and stuff, let's say we have a right triangle, and this is like 4, and this is 3, then we can use things such as the Pythagorean theorem to find out how long the hypotenuse is, and so here we'd get 5. But now in calculus, what we want to do is we want to try to find the length of like some smooth curve that can't be found using a geometric formula. So the way that we're going to do this is by taking a representative slice of our curve, and let's say that we're trying to find the length of the curve between x equals a and x equals b, just like normal. But let's focus on this little slice of the curve. So remember, the idea of differentiability is that I can take a small piece of a curved function and zoom in on it close enough until it looks like a straight line. Well, the nice thing is, once this looks like a straight line, I can superimpose this triangle on top of it. And this triangle, this black line, will have a slope, and the slope will be equal to dy dx. And because the slope is basically just rise over run, that means that this blue height is dy, and this blue base is dx. And so, in fact, because I've zoomed in close enough and the black hypotenuse looks like a straight line, I can use the Pythagorean theorem on using dx and dy. And so the length of this little hypotenuse is the square root of dx squared plus dy squared. And now, as you might presume, to find the entire length between a and b, I'm going to integrate this between x equals a and x equals b. And you might be wondering to yourself, surely this isn't right, because before we had like some dx here in order to integrate it. Well, when we do arc length, there will be a dx here, but we can't just write it in. You can't just make things up like that. Remember before with volume formulas that the dx represented the width of the representative rectangle, or the width of the washer, or the width of the disk, and that sort of thing. Whereas here, to find this length, the length is the Pythagorean theorem, and so that we can't just throw in a dx. So what we're going to do is we're going to algebraically manipulate this to make it nicer to integrate. So I have my integral from a to b, and what I'm going to do now is to factor out a dx squared from both of these terms. So I'm left with 1 plus dy squared divided by dx squared. And now, using properties of square roots, I'm going to pull this dx outside, and in fact I'm going to pull it out to the back because that's where we're going to write the dx. So my integral is now a to b of the integral of 1 plus, and now here, notice that I have squared and squared, so I'm going to pull the squared out of the dy here and the dx, so I have dy dx and then squared. And then this dx I pulled out, and so that's outside the square root at the end. And just to rewrite this in a format that you might see more often, integral a to b square root of 1 plus, and then here, this term again, hey, what is dy dx? Well, dy dx is simply f prime. So really we can think of arc length as the integral from a to b of 1 plus f prime of x, and then you do have to square f prime after you take that derivative, and then you have your dx at the end, like that. So that's our arc length formula. Let's look at some examples of just setting up the integral, and then we'll worry about how to evaluate them later in class. Let's say that we have the function y equals x cubed over 6 plus 1 over 2x, and we want to find the arc length from 1 to 2. So if I were to draw a quick sketch of this graph, I used a calculator, but it looks something like this. And so we imagine that for doing arc length, essentially you're taking a piece of string and you're overlaying it on top of this curve function, and then later flattening it out and finding the true length. But now using calculus, we can simply set up an integral to represent this. So the first thing I'm going to do is find dy dx. I need to find that f prime because that's going to be used in the arc length formula. So here the derivative of x cubed over 6 is going to be 1/2 x squared. And now this 1 over 2x I'm going to rewrite as 1/2 x to the negative 1, bringing the negative or the x up to the top, and I'll have minus 1/2 x to the negative 2, which I can rewrite as, let's see, we'll have x squared over 2 and then minus 1 over 2x squared. So that's my derivative. And now to write my integral, L equals the integral from a to b. Well, a and b are given. It's just simply 1 and 2, which is very nice and convenient. Square root 1 plus stuff squared, and the stuff is simply the derivative that we had just found. So I can throw in the x squared over 2 minus 1 over 2x squared, and then put a dx at the end, and that would be the length of my integral, which I can now either choose as a multiple choice answer or evaluate on a calculator. There are ways of doing this by hand, but we're not going to focus on them as much. Now sometimes you might need to simplify things before you can find the correct answer, or to make the integral easier. Let's say that we have y equals ln of cosine of x, and we're going to go from 0 to pi over 4. Let's go ahead and find that y prime, because we'll use it later. Alright, so I have natural log of stuff, and so the derivative is going to be 1 over stuff, and then I'm chain ruling cosine to get negative sine x. And then this gives me negative sine x over cosine of x, which is simply negative tangent of x. So that's that y prime that I'll use in my arc length formula. I can go ahead and start writing it since it's basically plugging stuff in. My a and b value are 0 and pi over 4 because that's the interval. Nope, not pi over y, it's pi over 4. There we go. Square root and then 1 plus stuff squared, and that stuff is simply going to be the negative tangent of x. I'll throw in a dx at the end because that's the formula. And then here I can in fact simplify this using some algebra and trigonometry. So I have negative tangent squared, which is just going to be tangent squared, so I'll have 1 plus tan squared x dx. And then if you recall, there is a trigonometric identity that says that 1 plus tangent squared x is really just secant squared x. And so because I'm taking the square root of secant squared, I'm going to end up with the integral from 0 to pi over 4 of secant of x dx. Technically speaking, because the square root always returns a positive value, and secant squared, actually secant squared doesn't have negative values, but secant does. So to be very careful with this, I could put absolute values around the secant, and then take that into account when I plug in my limits. But this would be the answer you would be looking for. So yeah.